We're finally ready to slot in the last important piece in the puzzle of writing a efficient lexical analysis engine. Essentially, how can you implement LEX, right? So we started off with this notion of regular languages, and we saw that there was a fairly easy way to define the set of strings that correspond to the regular languages. And then we saw the notion of a regular expression. And we saw that the notion of a regular expression, the meaning of a regular expression can be expressed as a set of strings. And those set of strings, each of those represented a regular language. The next thing we saw was the algorithm to accept or reject a string. So if there was a string that belongs to the language of a regular expression or a string that did not belong to a language of a regular expression, we sort of used a notion of a finite state machine to provide an accept-reject algorithm or recognition algorithm. And now the last step is the one that is the topic of this fifth video lecture, LEX5, which is how do we take a regular expression and convert it into a non-deterministic finite state automata. And the reason we would want to do that is to use this recognition algorithm in order to implement our lexical analyzer. So in order to build a lexical analyzer, we start first with the notion of a token, and we define what that token should be using a pattern, right? So we look up the language specification, or if you're writing the programming language, you write down a pattern that's supposed to describe this token. So if it's an identifier, we decide what should be an identifier in this programming language and write down the pattern for it. We take that pattern and then write down a regular expression that is equivalent to that pattern. So the assumption here is that your programming language doesn't have kind of weird patterns that cannot be written down as a regular expression. Like your identifiers shouldn't be palindromes or have matching parentheses or something where it's impossible to write a regular expression. So that's kind of a trade-off. You can say, we'll give you a compiler tool that makes it easy to write a lexical analyzer. In return, you should make sure that your definitions can be written down as regular expressions. Once we have a regular expression, we want to convert it into an NFA. So this is the topic of this lecture. We're going to see how we can do this. And we already saw how we can take NFA and convert it into, take a non-deterministic machine, convert it into a deterministic machine. And then a DFA is really easy to then match or reject strings corresponding to that token. And there are some efficiency issues that we are not going to cover in this lecture. There'll be the topic of some extra slides that don't have video lectures. So one is on the topic of minimizing the number of states in a deterministic automata. And there's some efficiency considerations, like how can we write a very fast implementation of matching strings using a DFA. But for this lecture, we're going to focus on this topic here. If I have a regular expression, how do I convert it into a automata, in particular a non-deterministic finite state automata? We are going to use what's called Thompson's construction to do this conversion from a regular expression to an equivalent NFA. And there are 6 simple rules. The empty language, each symbol in the alphabet, the empty string, alternation, so like R1 or R2, concatenation, which is R1 followed by R2, and then repetition, which is the usual star operator. It's called the Thompson construction after Ken Thompson, who first came up with this algorithm for actually doing search in a text editor called QED back in 1968. Okay, so Thompson rule 0 is for the empty language. So essentially this accepts sort of no strings. It's for the empty language. So it's just a base case. It's not particularly useful in practice because usually we want to accept something. We don't really have tokens that define the empty language. We optionally include a sinkhole state. A sinkhole state is just a state here. So this state over here would be called a sinkhole state because every symbol in the alphabet goes there and it keeps accepting stuff. And the important thing is that this state is not a final state, right? So it just keeps reading input strings. You can think of it as a sort of garbage collection state. It just collects all the characters and doesn't accept any string at all. Thompson rule number 1 is sort of the base case. For every symbol X of the alphabet, there is an NFA that accepts it. That's a very simple NFA that has a single start state. It has an edge on the input symbol X, and it reaches a final state. So if I have a language containing a single string X, then this NFA is definitely going to recognize that set of strings, right? So this set of strings containing one symbol X is, as you can see, equivalent to this NFA, right? Just by construction, you can see that it's trivially true. Now, when you have an empty string, we can create an NFA that accepts only the empty string epsilon by having, again, a start state, and we can have an NFA that accepts only the empty string epsilon by having a start state, a transition on the empty string, and it reaches a final state. So that's basically accepting a language which just has the empty string in it. Thompson rule number 3 is the one that's sort of more interesting. It starts building up bigger, more complex NFAs based on simpler NFAs, right? So it's recursively building up larger and larger NFAs. And the rule number 3 is about alternation. So if I have, so we are assuming, just like when we do in recursion, we assume that we already have an NFA for R1 and we already have an NFA for R2. So those could be based on any of those base cases I showed you. Like it could be one symbol, for example, or it could be a complex regular expression that I've eventually converted to an NFA. And then I'm trying to do R1 or R2. So I take the NFA for R1, and this rule number 3 is telling me how I can build a NFA for this alternation. So if I have the NF, so this is the NFA for R1, this is the NFA for R2, right? Then what I can do to accept R1 or R2 is create a new start state, and then I have 2 transitions on the empty string that go to the original start states of R1 here and R2 here, right? So we take this transition into R1 and R2 on this empty string. So this essentially counts as this alternation, right? It says I can either go to R1 or go to R2, and the final state of R1 has a transition on the empty string to the new final state, and the final state that was for R2 has a transition on the empty string to the same new final state that's over here. So notice that I can take either this path or I can take this path, and that is the definition of R1 or R2. So I can build a bigger NFA that accepts this alternation. The same idea, but for concatenation, is the topic of rule 4. So if I have an NFA for R1, so that's over here. So let's say I have an NFA for R1, I have an NFA for R2, I want to concatenate them together, then what I would do is take the final state of R1 and then connect it to the the start state of R2. So I'm taking R1 and I want to make sure that all the strings of R2 can follow R1. So I just create this transition to link them up together. And then I can, so this is the final state of R1. It should no longer be the final state because it should finish with the strings from R2, right? So I remove that notion that this is the final state. It just becomes the ordinary state here. And the start state of R2 again becomes an ordinary state. It's no longer a start state because the start state starts over here with all of the strings from R1. So it's really straightforward to combine them, and the key is to combine them using this empty string, the epsilon move. The rule 5 is about the star operator or the Kleene closure. So if we have an NFA for R, so that's shown over here, then I want to represent this operator star, right? So star means, as you know, 0 or more repetitions. So if there is a language of R, I want 0 or more repetitions of every string in this language. And so the way to ensure that is to again use the transition on the empty string. And so what I'm doing is I create a loop back that goes from the final state back to the start state. So I can iterate, 1, twice, 3 times, as many times as I want. I can loop through this finite state machine to get R star. And remember that R star also includes the empty string. So it also includes 0 repetitions. So in order to deal with that, we have this special transition that completely bypasses the NFA for R, and it goes directly from the start state to the final state. So notice that what was the final state in R is no longer the final state here because there is a new final state. And it's linked by this empty string transition as we did for the other sort of combinations of NFAs before. And the new start state is linked with the empty string to the start state of R, which is here. That's the old start state of R. But notice that it has this sort of escape hatch of going directly to the final state. So it'll accept the empty string. It'll accept all of the strings that were in the language of R once or twice or 3 times. Every time I take this loop back, I can take another sort of copy, another string that belongs to the language of R. I can make another one, and so on. So let's take an example. Let's take the set of all binary strings that are divisible by 4. So we want to, just for the sake of keeping the regular expression a little bit simpler, we're going to include 0 in this set. And so it is defined by this regular expression. So as you can see, this defines a set of strings. And if you look at the language of this regular expression, it is including 0, right? It includes 0, 0. It includes 1, 0, 0. And then it can have 1, 1, 0, 0. It can have 1, 0, 1, 0, 0, etc. And if you look at all of the strings in this language, and you take out the zeros from it, it's all the numbers. If you convert these bits, these binary strings into decimal, you'll see that it's all of the strings that are divisible by the number 4. So, that's just to show you that regular expressions can be used to represent lots of things. Now, the main reason for this example is to apply Thompson's rules to take this input regular expression and create an NFA. And if I then give that NFA one of these strings, it should be able, it'll tell me, yes, this string belongs to the language of this regular expression. So we saw that already in the last video lecture, how we can do a recognition algorithm that accepts strings that are in this language and rejects strings that are not in this language. So it can be used as an acceptor of all of the binary strings that are, if you convert it to decimal, are divisible by 4. So let's start with the construction. Always starts with the basic blocks, starting with the symbols in the alphabet, right? So we're going to start from the very simple sort of single element or single symbol strings, and then grow to larger and larger substrings in this regular expression. So if I look at just the NFA for 0, that's really simple. It's this NFA over here, and the NFA for 1 is over here. So we're going to use the NFA for 0 and 1 for all of these cases, right? We're going to use it here, here. The one for 0 is going to be used in all of these instances as well. Now, if I want to combine a 0 or 1, so this part of the full regular expression, then I can use the Thompson rule for alternation, and I create a new NFA. So I take, remember, this was the NFA for 0, this was the NFA for 1, and then I just put a new start state and a new final state, and I put the appropriate empty string transitions, and now I've created a new NFA that recognizes either 0 or 1. If I want to do 0 or 1 star, which is this part of the original regular expression, then if you remember, we started off with this. Here was the original regular expression for 0 or 1, and then I take this transition over here on an epsilon that does repeated loops and produces either 0 or 1 as many times as I want. And then there is a special start state and a final state, and the way to bypass that entire loop. And it goes, if you want the empty string, you would take this transition over here. So if I look at this NFA over here, this NFA now is equivalent to 0 or 1 star. And you can see why, right? If I wanted to take a string that's in this language 0 or 1 star, so let's say it's 1, 0, 0, 1, something like that, then I would take this path to take this one here, and then I would go back and then take this path to take the 0, go again, take this loop again, take another 0 and another 1, and I can keep doing this. And at some point when there's no more symbols left, I would take this transition over here to the final state. So that's how we can get from 0 or 1. What we've done is constructed an NFA for 0 or 1 star. Now we want to add these two zeros, so that's corresponding to this part here. So we already have 0 or 1 star built. We want to add 0, 0. So the NFA for 0, 0 is just concatenation of the NFA for 0 and the NFA for 0 here. We're just concatenating them together. And I've just sort of done it in one step because it's tedious to draw it. It becomes quite unwieldy to fit it all in one slide. So I'm just doing the concatenation as a single NFA here. So this NFA here recognizes the NFA for 0, 0. Now all I want to do is take the NFA. So this is the NFA for 0 or 1 star, and I want to combine them together. So all I have to do is connect up this NFA with that one in order to it's doing concatenation, right? So I just do that additional transition. So all I did was link the final state, which is here, with the start state of this NFA 0, 0 with an empty string, and now I have the NFA for this entire string. Now the only thing left is this lonely 0 over here, So the NFA for this 0 is shown here, right? This is the NFA for 0. Now we can connect these two up using the alternation, right? So we're going to have to do the OR. So it's either this NFA that's over here, the NFA for, this is the NFA for 0 or 1 star 0 0, and this is the NFA for 0, and I just want to put an alternation between them. So all I have to do is add a new state and connect these up, and again so basically a new final state and a new start state, and the start states of the original one become ordinary states, and the final states also become ordinary states. So those are the changes we need to make, and which is what is done here. We start with this start state here. There's an epsilon transition to the NFA for 0, 1 star 0 0, and another epsilon transition to the NFA for 0, and then they're both linked to the new final state, which is shown here. So as you can see, it's really straightforward to take each of the rules and apply them to recursively build a larger and larger NFA for complex regular expressions. So we have to start at the right place. So if you see, what we did was we started with 0 and 1, and then we did 0 or 1, and then we did 0 or 1 star. So basically we were doing this kind of nesting dolls, going from inside out in building this NFA. So which order you build the NFA matters. Part of the algorithm needs to be aware of the order in which to build these smaller NFAs and then group them together, right? So that's the reason why we spent some time talking about how regular expressions are in fact trees, because for every regular expression, once you disambiguate it using precedence and associativity, you can take this regular expression that we have and think of it as a tree structure, right? So this Thompson's construction is going to take a regular expression, and the input it gets is not a string, but like a tree structure, and converts it to an NFA. So we're going to build the NFA recursively from the regular expression tree. So for this input, which is A followed by A or B followed by C, let's assume that someone has provided a fully bracketed regular expression, which means that we know what the tree structure looks like, right? So we can see that A or B is represented in this part of the tree here. So this part of the tree represents A or B, and then there is a concatenation with A, which is over here, and then there's a concatenation with C, which happens over here. So the tree structure is in fact telling us the order, the sequence of operations to use. You can also represent this tree structure more concisely by just using a post-order traversal of this regular expression tree, right? So you can take this tree and give the input to the algorithm the tree structure, but in postfix format. So I can write it down like this. So if you're familiar with postfix, essentially what it's doing is it's going through and traversing this tree all the way down, so depth first, and then every time it has 2 children, it prints out the 2 children, and then it prints the parent of the 2 children right after it. So in this case, this A corresponds to this A, this B corresponds to this B, and this OR is the parent of these two. So I know that this part of the postfix representation of the tree includes the fact that OR has 2 children, A and B, right? So when I'm constructing the NFA recursively, I can just read this postfix string from left to right and then construct the NFA recursively. Now we have the input. The input is the tree structure in postfix notation. And so to take this input, and what we want to do is take each of these nodes in this tree. So each node in this tree is representing one node that can be created by going from left to right in this string in postfix order, right? So, for example, N1 is the NFA for this input symbol A, and 2 is the NFA for this symbol A here, and N3 is this one for B. And now when I combine N2 and N3 with an OR, then I'm going to create recursively a larger NFA, right? So let's see how this process works. In order to do this, we're going to have to use a data structure that lets us keep track of the tree structure. So the input is this tree in postfix, and we also need a stack to keep track of where we are in this tree. Let's start by reading the regular expression. So the first symbol we're going to read. So remember that we've taken the regular expression that we started off with. We are representing the tree structure of the regular expression in postfix, and we're going to scan this from left to right and build the NFA for the full regular expression, sort of one symbol at a time. And in order to keep track of where we are in the tree, we're going to use a stack data structure. Okay, so first step is to create the NFA for the symbol A. So as you can see, we're starting from the leaves of the tree where the NFAs are the simplest. And then as we go up the tree, the NFAs will get more and more complex as we merge them together based on the operator. So either alternation, concatenation, star, etc. So the first thing we do is we push N1 onto the stack. So N1 is the NFA just for the symbol A. So it's a simple sort of base case NFA. Then the next thing we do is read the next symbol, which is A, and create another NFA N2, which looks identical to N1, but we need it to be a separate copy, even if it looks the same, because we're going to be merging them together to create more complex NFAs, right? So in this case, we push N2 onto the stack. So you can see now the stack contains the last thing. This is the top of the stack is N2, the last thing we pushed in. The next thing is we read B, and this leads us to create an NFA for B, which we'll call N3, and we'll push that NFA N3 onto the stack. So now the top of the stack has N3 in it. Now the next step is to process the alternation operator. Now we know that the alternation operator takes 2 arguments, right? So we want to supply those 2 arguments to the alternation operator so that we can build from 2 NFAs the NFA for the alternation. So what we do first is we pop its 2 arguments, which is N3 and N2, out of the stack. And so those come out of the stack and are given as input to the construction, the Thompson rule that constructs the alternation NFA, right? So in this case, it's sort of, just to remind you, if I had A and a B and I wanted to create A or B, I would create this more complex NFA by just adding these epsilon rules, making this the final state and this is the start state, right? So when I want to process this alternation, I would take N3 and N2, which are these 2 NFAs, and then create a bigger NFA. And that's what we do, and create N4. So any of the nodes that are internal are going to be taking arguments and creating a more complex NFA using one of the Thompson rules. In this case, the alternation creates the NFA N4, and then we push that N4 onto the stack. The next operator is concatenation. Concatenation also takes 2 arguments, and the 2 arguments that it needs are on the stack. So it pops out N4 and N1, and then combines them using the concatenation rule. So this is the Thompson rule that applies concatenation to N1 and N4 and creates a new NFA N5, which then gets pushed onto the stack. So the top of the stack is N5 now. And then the next step is to read the C. This is, again, a simple NFA just for the symbol C. It gets pushed onto the stack as well. And then the last operator we have in this postfix traversal of the tree is the concatenation between N5 and N6. So we pop out the two elements it needs from the stack, and we combine them using concatenation, which is done using one of those Thompson rules we saw before. For concatenation, creates N7 and then pushes N7 onto the stack. Finally, there is no more input left, right? So there's nothing here. So we are ready to pop the top of the stack. There should be only one element if we did everything right. And we pop that element, and since there's no more input and the stack is empty, we return N7 as the constructed NFA from this algorithm. So in order to again help you understand whether you understood, use Thompson's construction to build an NFA for this regular expression, which is 0 or 1 followed by 0 or 1 star.